Hello everyone, welcome to Introduction to Semiconductor Devices. This is lecture number 9. In the last lecture, we were talking about non-equilibrium situations in semiconductors. We introduced the concepts of minority carrier diffusion length and minority carrier lifetime. And we said that, these two parameters play a very crucial role in the response of semiconductor devices. So today, we will introduce a concept of Quasi Fermi levels. Quasi Fermi levels are very useful tools in representing non-equilibrium situations on a band diagram. Okay, so as we go along, we will understand what Quasi Fermi levels mean. Okay? Just to refresh your memory, we have seen these expressions before, right? So basically, N naught will be given by Ni times exponential, the distance from the intrinsic energy level, and similarly, P naught will be again the same thing. And let's say you have a semiconductor which is doped with 10 power 15 dopants. Let's say there's a arsenic or phosphorus dopant, so they are donors. You have an N-type semiconductor. So what would be the carrier concentration? Well, we have seen it multiple times. So N naught is going to be 10 power 15, and P naught equal to 10 power, let's say 5. In the class, I'm using it as 10 power 5. I'm using Ni as 10 power 10. Okay, the actual number is 1.5 into 10 power 10. Okay, so and whenever we have equilibrium situation, the excess minority carriers are going to be 0. Okay, so where will be the Fermi level in this case? Okay, so let's say I'll just do it one more time in case somebody is joining afresh. So EF minus EI, by rearranging this equation, I can write EF minus EI is equal to KT ln of N naught by Ni, right? So this would be KT into 2.303 into log of 10 power 15 divided by 10 power 10. Okay. So this would turn out to be, okay, this particular quantity here, KT into 2.3, will turn out to be exactly 59 MeV, okay, milli electron volts. So in the calculations that I do today, or in the subsequent classes, basically I'll take this KT into 2.303 as approximately 60 milli electron volts. Okay, this will simplify my calculations. I don't want to do exactly, but it will be close enough. 1 milli electron volt difference, but it will lead to some small error, but you can verify it. Whenever you need exact calculations or in the homeworks and assignments or in the exams, please use the exact numbers. I don't want to use a calculator while teaching, so I choose 60 milli electron volts. I'll approximate it that way. So the Fermi level, the distance of Fermi level from EI would be 60 MeV into 5, log 15 by log of 10 power 15 by 10 power 10 is log 10 power 5. So that's 5. So this will be 0.3 eV. Okay, so you could represent that on the Fermi. We have done this multiple times in the past. EF is going to be at 0.3 eV distance from the EI. Okay, as you increase doping, EF changes appropriately. Okay, so the message I wanted to convey is at equilibrium, EF captures carrier concentrations. Fully. So by which I mean, for example, I have used N naught expression. You could also use the P naught expression, okay, and calculate the distance from EI. Okay, if you use that P naught was 10 power 5, so you just use the P naught expression and calculate EF again. Okay, it will give you the same answer. The distance of Fermi level will be 0.3 EV above EI. You'll get the same answer plus, but please make sure that you verify that. Okay, so whenever you have an equilibrium situation, all you need is simply EF. If you know EF, you know all the carrier concentrations. Okay, so you don't need anything more. But what happens when I have a non-equilibrium situation? What do I do? Okay, whenever you have non-equilibrium situations, we know, right? We have seen this last class. So basically now N is going to be the total carrier density, which will be N naught plus the excess, let me put it as small, excess electrons, right? Excess electron density. And similarly, P is going to be going to be P naught plus delta P, right? This is what we have seen in the last class. And we said that N into P is not going to be equal to Ni square. So these are excess carrier densities that we are introducing, let's say by shining light. Okay? We could get situations like this. So we want to be able to represent this on a band diagram. And to do that, we define quasi Fermi levels, basically. So define quasi Fermi level. I'll simply call it as QFL just for short notation. So the definition we use is very similar to what we have seen in the normal equilibrium carrier density cases. So I'll simply replace equilibrium electron density by the total electron density. That will be equal to Ni times exponential. In the equilibrium case, we had EF minus EI. So now instead of EF, I'll put it as EFN minus EI by KT. Similarly, for holes, I will replace the equilibrium hole density by total hole density, and that will be equal to exponential. You might already be guessing here. So instead of EF, I'll put it as EFP by KT. Okay. So what I'm essentially doing here is I'm replacing N naught by N, EF by EFN, okay, and P naught by P, EF by EFP. Okay. So these EFN and EFP are known as quasi Fermi levels. Okay. So this is the definition. So EFN and EFP are called quasi Fermi levels. Okay. This is different from the regular Fermi level. So we saw that regular Fermi level is useful when you have equilibrium situations. Whenever you have non-equilibrium situations, we use quasi Fermi levels, okay, which essentially capture the total carrier densities. Okay, so this is how we define it. And why do we have two of these? In the regular situation, we had only one Fermi level, right? We don't have one Fermi level for electrons, one Fermi level for holes. Okay, in the equilibrium situation, we saw that either of the expressions will give you the same answer. Okay, but if you go to non-equilibrium, we see that it doesn't work, and we have to use what is known as quasi Fermi level. Let's take an example. The same situation. Okay, just note I have replaced here in the expressions, instead of N naught, I'm using N, and then I'm using EFN, which is a quasi Fermi level for electrons. Similarly, P, and then quasi Fermi level for the holes. All right. So now consider the same situation. You have a doping density of 10 power 15, but now I have electron and hole excess carrier density as 10 power 17. Okay, I'm introducing it by, let's say, shining light. Okay. So we also saw that the Fermi level, the equilibrium Fermi level EF, was basically 0.3 eV above EI, right? So now where will the quasi Fermi level for holes and electrons be? Okay. This was EF. Okay. So to do that, let's estimate. In the equilibrium case, of course, you can, if you substitute the equilibrium carrier densities in the expressions at equilibrium, delta N equal to delta P equal to 0. Therefore, EFN equal to EFP equal to EF. Please, try to substitute these numbers and check it out. It will turn out to be this. Okay, this is an equilibrium situation. But now, when we want to talk of non-equilibrium situation, so we have what is the N? N is going to be N naught was 10 power 15 plus delta N is 10 power 17. So this will be approximately 10 power 17. Let's take it to be that. Okay. Okay. By the way, I'm always ignoring the units, but please make sure that units are right. 10 power 5 plus 10 power 17. So this is also going to be equal to 10 power 17. Okay? This is the carrier density. Now, where will be the quasi Fermi level? We use the same approach as we taken for the regular Fermi level. So EFN minus EI. Now I'm just going to write away, okay, KT ln of 10 power 17 divided by 10 power 10. And we saw that that will turn out to be approximately 60 MeV times 7. 7 orders of magnitude change is the carrier concentration. So basically 7. So that will be how much? This will be exactly equal to 0.42 eV. Okay. So the quasi Fermi level for electrons is at 0.42 eV from EI. Similarly, you could do a calculation EI minus EFP. Okay. This will be KT ln of 10 power 17 divided by Ni, which is 10 power 10. So again, this will be equal to 0.42 eV. Same calculation. So what this is telling us is, whenever you have non-equilibrium situation, we can represent that by quasi Fermi levels. Now for this case, this quasi Fermi level I represent it somewhere here. The distance is going to be 0.42 eV. Similarly, there is a quasi Fermi level for holes. This distance is 0.42 eV. EFP this is, and this is EFN. So the conclusion what we are saying is, the EFN and EFP need not be the same when you have non-equilibrium. Okay. So the conclusion would be non-equilibrium is represented by two, let's say, quasi Fermi levels, EFN and EFP. Yeah. So, I mean, people get confused. Students sometimes get confused. It is simply a tool for us. Even Fermi level was a tool to represent how the carrier densities are in a semiconductor, right? So it might not serve. You may not see it. Right now when you look at this, just two levels. Uniform semiconductor. What does it matter? But once we have a device with P and junctions and all that, this becomes very useful tool for us to visualize. Just by drawing the diagram, we know what is happening in the device. Okay. So band diagram. So yeah, this is the definition. Let's take another example. Okay, this is the first case. Let me take another example. Now I'll retain everything same in the problem, except that now I have changed the excess minority carrier densities to be 10 power 10. Okay. So now what happens? So now you'll see that n is equal to 10 power 15 plus 10 power 10. So that's going to be 10 power 15. Okay. And P is going to be 10 power 5 plus 10 power 10. So that's going to be equal to 10 power 10. Right. So where will the Fermi levels be? We can easily compute that. Let's say EFN minus EI is going to be now. Okay, I'm writing the answers. Please, if you're unsure, stop it, go back and verify and make sure that you get it right. Okay. Into 5, that is going to be 0.3 EV. EI minus EFN is going to be what? 16 MeV times log of 10 by 10, log of 1, 0, right? This is going to be 0. So basically, what this is telling us is the Fermi levels have become. Okay, I will not draw the EF, the regular equilibrium. I'll draw the. Oh well, yeah. Let me actually put even EF. There's no harm. So EF. Okay. Now the quasi Fermi level for electrons is also at the same location. Remember, see, you are getting the distance from the equilibrium. Sorry, the intrinsic level is 0.3 eV. So basically, what we are seeing is EF equal to EFN. Okay. And what about the quasi Fermi level for the holes? Sorry, I should have written this. P here. This is for P, EFP. You see that EFP, the quasi Fermi level for holes, is equal to the intrinsic carrier density. So your EFP is going to be here. Okay. So what does EFN equal to EF mean? Okay. So we say that EFN equal to EF, right? What does it mean? It implies that electron concentration, okay, is not significantly perturbed. Significantly perturbed by the excitation. So you are essentially having electron hole pairs created by light, and that excitation is not really changing the electron concentration. That's why EFN equal to EF. Okay, and the EFP is changing. Okay, in the previous example, when the concentrations were 10 power 17, EFP was much closer to the EV. So basically, as the excess carrier densities increase, EFN goes towards. Okay, so let's say we can even conclude this, right? As delta N increases, EFN moves closer to EC, and similarly, as delta P increases, EFP moves closer to EV. Okay, so vice versa. I mean, it's exactly what you would expect with a Fermi level, but you know, in N type we said Fermi level will be above EI, P type it will be below EI. Now, even in N type semiconductor, when you have a excess carrier densities, you could have EFN and EFP, which are exactly the same expressions, just the definition is slightly different. We are taking the total carrier densities into account. That's it. Take one more example. Let's say delta N equal to delta P equal to 10 power 7. Okay, so I'll cut the story short. I'll say EFN minus EI is still going to be 0.3. Okay, whereas EI minus EFP is going to be 60 MeV into log of 10 power 7 divided by 10 power 10. So that's going to be minus 3. So that's going to be minus 0.18 eV. So now what it's happening is, as you are reducing the excess minority carrier density, you are moving closer to EF. So now in this case, the third case, right, I'll put it in the red here. So it is somewhere here. This was EFP for delta P equal to 10 power 7. So you see, we have seen in the previous case, right? Last lecture, that as the excess minority carrier concentration reduces, the sample approaches equilibrium, right? So we can conclude that as sample approaches equilibrium, EFN and EFP approach EF. Okay, so we said that already, right? Because we said there is no physical reason. I mean, if you see the way the quasi Fermi levels are defined, At equilibrium, both are equal to F.